Right. So today's session is going to be all about network analysis. I'm going to give you a guided example of guided use case of a network analysis on the metadata of the migrant stories corpus that you've already worked with and know well. The goal of today's lecture is to help you get going with network analysis for your own research. That means know what sorts of questions it can answer, where to start, and what to expect. It's going to have twofold perspective. The first is general key concepts of network analysis, and the other one, which is going to be stronger, is their implementation in the Gephi tool. Gephi is an open source platform for network analysis and visualization. We are going to talk about what constitutes a network, how we can map different variables from our spreadsheets to different elements of the network, about different network layouts that are algorithms that shape different sorts of diagrams for your network, and what they possibly are good for, what they emphasize, and what they suppress. And a very important part of this is network statistics and filters based on the different network statistics, because these are this is where you can ask the network to give you nodes that are in, or nodes or groups of nodes that you find interesting in a number of ways. Just to get on the same page, this is the metadata from the migrant stories that you can easily call from its Tatok installation. You see a table where each row represents one story. That means one speaker or one file. The first column is the ID of the file. The second column is the name of the speaker. Then we have the gender, and then something about the countries, the origin country and destination country. So each person has an origin country and a destination country, and now each country of origin and each country or destination lies on a continent that listed there. And we also know in some countries what their GDP per capita is, so that's a proxy for the wealth of the population of the country. And we also have let me see here. We also have a column that is a categorical variable. That means strings, that tells you about the difference in the wealth in the between the source or origin and the destination country. So, for instance, this person, file number 709, named Mung, from Vietnam, she traveled to Canada, and the change was age, which means high. That means from a low GDP per capita country to a rich country. Other levels are E, like equal, and low. That means that the person moved from a rich country to a poor country. And that would be about the columns we are interested in. And what we are heading for is a network graph of this metadata. How this is going to be shaped depends on our research question. Anyway, at any rate, a network graph is constituted by nodes, which in this case would be the countries, and edges, which which in this case are the trips or the paths from the origin country to the destination country. And in my network here, you see arrows, which means that the graph is directed. Directed graph in the directed graph, it plays a role whether, well, which direction you go, but it's not necessary. You can as well not care about the direction, and then you would have no arrows there, and it would be an undirected graph. So that's the building stones, nodes and edges. Now, if we go back to the data, we have a spreadsheet that depicts individual migrants. If we picture this as a network, then we would get the thing to the right. That means each rhomboid here would, each rhomboid would connect two countries. Actually, this person goes from this country to this country, and this person goes from this country to this country, and from this we could, here is no, not an error. Anyway, so here we could read that this country is very desired, or this country is very desired as well, with more incoming arrows than outcoming arrows. But isn't this far too complicated? We would have to we would have a so-called two-mode or bipartite network with two sorts of nodes, while the information we get anyway is information about countries, right? So let's focus on the countries and model anything that concerns the people as attributes either inside the nodes or in the edges. I would suggest that we focus on finding the most desired destination countries and how to define them in terms of network statistics, or the most common origin countries. That means that the countries most abandoned, or the most common paths, so where people travel most. That said, that means that we are going to focus on building a network like you see to the left-hand side, with just countries in. All tools for network analysis I know require two inputs, and that's a list of nodes and a list of edges. Gephi, the tool we are going to work with, requires them in form of two spreadsheets. And this part of the lecture is going to be about how to create these spreadsheets. So we have that spreadsheet that you saw before, with the columns text ID, country origin, country of destination. They lie on continents of origin and continents of destination. Then we have the gender information, those GDP columns, and I added some and names. Sorry, and I added some to make the work smoother for the purpose of putting it into Gephi. Gephi needs all nodes to have a label and an ID. The label can be the same as the ID, but anyway, it requires two columns that are called exactly ID and label. In the first step, I thought I would just have the country's ID as the abbreviated country name, and then have a label for each person, something like the gender and the text ID, because I can't use the name, since we can the data can contain different speakers that have the same name and gender. So it would have been something like this: a female from the file 308, a male from 111. But we just settled on not using the individual speakers. So actually, we can drop this label column right away. Now we want to save somewhere the information about the number of people that traveled from a country to a different country. So if we imagine it as the arrow, so to have a label on the arrow saying there were 3 people going from Vietnam to Honduras, for instance. So we have to have a column for that. We can make it gender specific, or no, not gender specific. And the fact that we have several genders would make it complicated again. So let's drop the path gender column as well, and let's only use the path no gender. That means we are not interested in how many women went from Vietnam to Honduras and how many men, but we will have one common arrow saying there were just, no matter the gender, migrants from Vietnam to Honduras. In my program, it looks like this. You can do the same thing in Google Spreadsheets or whatever spreadsheet program. Now we are so we have a frequency table that's not going to depict each row at the end. Each migrant in the end, but we are going to use only the numbers. They are numbers. In my sorry, now it's going to be lengthy. In my table, I added the number of all people traveling from Vietnam to Canada, just like another column, and then I duplicated the rows. You can do it differently as well. Anyway, we end up with not 709 name Ngung, or what her name was, but we would have something like Vietnam, Asia, Canada, North America, GDP change, path no gender, and there would be the number of people who traveled that path, and yeah, the GDP column, GDP change. And from that, we will create the table of nodes. So we have to take all countries, no matter whether they were origin country or destination country, and we have to list them like this. These label and ID would be the absolutely necessary columns to have. And as I said, it doesn't matter that the label, which is the abbreviated name of the country, is the same as ID. Then I also added 2 columns, an abbreviated name of the continent of that country, and the GDP information. And the GDP looks very very suspicious, very suspect, because from three random rows we get 3 times no value here. So we'd better look how much of this information we actually have, and whether it is worth it at all to capture it here. So we see that we have 120 NAs, and here we have the minimum GDP per capita something above $100, and this would be almost $1,000. That means that's pretty low. So this would mean that we absolutely don't have the rich countries. I can tell you that there are 142 countries in the data, and 120 of them are NAs. So we should. This is just reasonable to drop this column because we can't get information of much value here. So we end up with continent, label, and ID. Now the edges table. We have to know. We have to have two columns, which are these are absolutely obligatory, and one is called source, and the other one is called target. And in these columns, you must have the IDs of the nodes. Since our IDs are the same as labels, we can't see a difference. So these are IDs of the source and of the target nodes. Then we have a third column that is not obligatory, but what comes in here will be by default mapped, like used as a third variable. And that's the number of people, in this case, that's the number of people going this path. So we have one person who traveled just within Chile. We have two people going from the United Kingdom to Honduras, one person going from Greece to France, etc. And we also have the GDP change, since unlike the GDPs for the countries, this is pretty. This doesn't have any NAs, any empty values in it. So that's a valuable source of information, and let's just keep it for the future. If you were following the instructions for this course, there you were asked to install all this software. So if you did your homework and installed Gephi, now would be the time to open your installation of Gephi, so you can follow live with what I'm going to present on the slides. You can download the working file for Gephi here on our website. Here in the under today's lectures materials, and the presentation, by the way, is here as well. So let me introduce Gephi to you. That's the Open Graph Viz platform. It has a nice website. It has a client that you can install, a local client, and it starts. It's just released an online viewer of Gephi based or Gephi produced graphs. But we are not going to go to work with that, because we have more than graphs. We have. I'm going to present you a whole project with all the guts inside, and the online platform cannot display it yet. So this is taken from the website of Gephi. They have a number of excellent tutorials there. So you can, once you start working with Gephi, you can learn a lot about how to use it and about the network analysis in general there. I just hope to give you a solid start so that you are not lost at the beginning. When you open Gephi, you are going to see something like this. when you open a file, then there are going to be to appear three tabs: Overview, Data Laboratory, and Preview. And there will be, so this is the three main views on anything you do in Gephi. This is the place where you import your CSV tables. Here is the place where you explore the graph for yourselves. And here is a view where you can tweak what you have done in the overview and export it as an image file. So this one is interactive, this one isn't then anymore. So here you open a new project or some other project, or in your case, you can just double click on the file and say that you want to open it in Gephi. And we start in this data laboratory. Once you click on anything of those, Gephi will open a workspace for you. So there's a project and a workspace. You should name your workspace like this, so that you can keep track of what you're doing. In one project, you can have as many workspaces as you want. This is very handy because when you are just messing around, you easily lose the track and are not able to return to what worked before it ceased to work. So I would recommend you to copy the workspaces before any major change and just try out the change in a different workspace. In the workspace, once you have named it or not, you see a tab called Data Table. And the data table actually waits for two tables, the nodes table and the edges table. Now it's focused on nodes. So the import spreadsheet expects to get a spreadsheet with at least two columns called ID and label, because these are the nodes. It can happen to you that this view is missing. That's because you can manipulate the panes here. This data table is a pane, let's say, a square. So you can add more panes or squares to that, or let them disappear. If you accidentally destroy this or let this disappear, you can always find all those tabs here in the window menu. So this is a drop-down menu that offers you everything you can work with. And what you just lost here was the data table. So when you click this, you will get it back. Now you have your data table back, and you are going to import a spreadsheet. So you just import it. Here you can again select whether it's the nodes table or edges table or what it is, and it has two steps. That was the first step, and the second step is that it wants the label and ID column. So you should check that it has that, and then you can tell it what sort of data, whether it's string or numbers or whatever, the other columns, the optional columns have. we don't need time representation here, so I'll just skip talking about this. And that's the final step, well, third step, where it asks you about the type of the graph. Our graph is directed because we want to model from where to the people travel. And we want to append this to the existing workspace. We don't want a new tab here. As you can see, meanwhile, I named my workspace countries 01. When edges go both ways, I choose to add them, although there are also better strategies to do that, to merge or not merge edges. Gephi shows you then what it's going to import, well, what it imported actually. And you see here the ID column, the label column, then the continent and the GDP. We do the same thing with the edges. So it's an edges table, comma separated. Here we have the source and the target, and it recognized the weight. Well, didn't recognize the weight yet. And the GDP change column. In the second step, it's going to recognize the columns. So source okay, target okay. Then it wants to know something more about the weight. So we say it's a double. Double means that it's a continuous variable with numbers that can be decimal numbers. And the GDP change is a string because it's that high, low, equal. Again, it wants to know what sort of graph this is. So we have a directed graph. We want to normalize the scales, the weights, so that we don't have very big differences, or that we have them all on the same scale. And I ticked here that I also want to see self loops, so that we can see how many times it happened that someone traveled within the same country. And again, the same edges merge strategy, and we append it to the existing workspace. By that, we have the edges table here. It looks like this. I don't know why it combines the source and target label with the ID and creates its own ID, but never mind, it's going to work. And this is the weight. Weight means how many people traveled that path. So we know that there are 30 people who traveled from Syria to Greece, and that the change of the GDP was from low to high. So we are done with the data lab. The next step is that we are going to see the graph. That all happens in the overview pane. It always starts with such an ugly square where you can't see much. And I'm going to show you how to tweak the graph so that you actually can read something of it. Again, it's overview, not preview. If you failed to see the graph in the overview or have a mess of panes here, then you can let them all disappear by those crosses, and then choose in the window which you want to see. This is always called the graph. So it has some the graph pane has some convenient options here, like whether you want to show node labels here. So let's do that. And you can choose how they, well, the font and their size, and whether the size is going to be fixed, or if you zoom, you can zoom it out on the graph. So whether you want the font size to remain the same no matter the zoom, or whether it should react to the zoom, and how you have to play around a bit to find out what just suits to your need at that time. It also has something with edges. So it's about the edges color and whether edges should be visible. And these are the labels of the edges. We don't have any labels there right now. What is more interesting from the data analytical point of view is the variable mapping. The weight, since and that was the number of people, no matter the gender, who traveled that path. The weight was a numeric variable, the double. Then it gets automatically mapped on age thickness. When you look here, then you see already in this ugly graph that the edges, that the arrows are have different size, different thickness. We can then we also can map something on another variable on the nodes. So the nodes can be colored or have different size according to some other variable. This is done in the, again, still the overview, in the appearance pane. And when you open the appearance pane, then there is a menu for nodes and a menu for edges. They look the same, and they offer you color and size of the node or of the edge, and then a color, then the color and size of the label. Then this is interesting as well. This unique partition and ranking means unique means that all nodes or all edges are going to have this color or this side or these features of the label. When you click here on the color, you are going to see a color wheel, and you can select a different color. So unique is just all nodes without mapping a variable there. If you want to map a variable, then you use partition and ranking, depending on whether your variable is a categorical variable or a continuous variable. If it's something categorical, then you choose partition. If you partition the colors on nodes or on different categories of that variable. In our case, that's the continent, or it could as well be the GDP change, because these are categorical variables that have only a certain number of values. If it's then you just choose it and change and select apply, and then it's going to appear there like this. So here I have the continents. See that Senegal is Africa, Pakistan is Asia, etc. The same goes for edges. You can, if you have a categorical variable on the edge, like we have the GDP change, that's something that happens not inside the node, but on the path, right? So so you can color the edges as well. The same goes with for ranking on nodes and edges. So let's say the GDP is that's a continuous variable, and we can map it on nodes or on the labels. So here I did both. Only you see that we have that is very misleading because evidently we only got some African countries, numbers for African countries, and I said before all NAs should have very low values, and then even very rich countries are small like this, and the richest country here would be Yemen. So we can't really use this. This is just to show you how you can map a ranking variable or a continuous variable. So that's how you can play around with the preview, with the appearance, with mapping the variables, coloring the nodes, coloring the edges, or changing the size of the nodes and edges. Now let's talk about the graphs themselves. So far, we still have the ugly, very dense square there, and we would like to have something more legible. All these graphs that Gephi creates are created based on algorithms. These algorithms are based on distance matrices of the nodes, and these matrices, the distances are different numbers. It could be the number of people on the paths. It can be some frequencies. It's very diverse what they use, and the algorithms differ. You can see them as functions functions that differ, and they differ in the approach to nodes, what sort of nodes they try to squeeze together, attract together, and what sort of nodes, or like nodes with certain relations between them, they try to repel. Gephi offers you some full-fledged layouts that just create original graphs. The three ones that you get like built in Gephi are Fruchterman Rainbow, Force Atlas 2, and Yifan Hu. And then you have a few like additional or secondary graph algorithms that take these big algorithms and just tweak them. Don't compute anything much more about it, but they expand the distances between the nodes, or they squeeze or they squish they contract the nodes as well as and you can tweak the diagram with that. For changing that square, you need to open the layout pane. Again, if you don't have it, just go to the window and open the window, or window is it called? So the pane is window. Open the layout window, and here you have a drop-down menu with the algorithms to choose from, and each algorithm has many coefficients here that you got parameters that you can fiddle with. Mostly, it's about how many times it's going to run how many times it's going to run, or how strong you want the attraction to be, or the repelling power to be. As you see here, this is the Force Atlas 2. that's a general starting point for large networks. What it does is that it brings together connected nodes and squeezes apart the non-connected ones. It may remain very shrunken, especially when you have a weighted graph with very different weights. Then I have to squeeze it apart, and I used the normal. I was normalizing weights, and I was increasing edge weight influence, decreasing gravity, dissuade hubs. It's somewhere. I think I just have not displayed everything correctly here. So sorry for that. This is a classic layout called Fruchterman Reingold. It's very neat, but it doesn't work very well with very packed data. The last one I wanted to show you was Yifan Hu. This one is designed to show you clusters. So you see here that it pulled or pushed out something that could be a cluster. Niger and these African countries where pretty much of the migration is just from each of those countries to each of those countries. That would be a cluster if we were identifying clusters. So Yifan Hu is said to be good for emphasizing just the communities or clusters inside networks. And now these views are interactive. It's still here you can manipulate the graph, and you can and then from there when you have manipulate the graph in a way that you like, then from there you go to preview, and from preview you can export it. You can as well make very conveniently make a screenshot from the overview, and that's often I find it more legible than the preview. Anyway, you can drag nodes by just catching a node and you pull it out somewhere, and then the nodes it's connected with go together with it, and so you can sort of you can sort out things that you like preliminarily, then you can push a button and pull them back. So that's a nice feature here. It's different sorts of dragging and selecting parts of the networks are here in the graph menu, in this stripe here, or this tool line, tool ribbon. And this would be the preview. This is how a network could look like when you export it, and you are happy with it. I am not saying it's the prettiest network in the world, but that's about how it's how it's going to look. So you had some settings of colors and labels and sizes in the overview, and you have seemingly the same thing in the preview. Now we are in the preview. That's where you export from. However, it's based on the overview. So some things that are not like really that don't map on the data, you can easily change here. but for instance, the coloring of the edges, you can override that one you have in overview by saying, I don't want this to be by the GDP change, but by something else. But by default, you are going to get, I don't know the default, but you can choose whether you want to preserve what you created in overview or whether you want something else. And now let's go over to the statistics and filters. By statistics, I mean actually additional columns in the CSV file you gave Gephi, where you would that would enable you to find interesting nodes or edges. And in practice, finding also means keeping those interesting ones and getting rid of the uninteresting one. So statistics in the graph means that you can reduce the clutter in the graph, that you get fewer nodes and edges, and it's going to be more intelligible. So what are the common statistics in networks? I'm only going to pick a few, and all of those will be node-wise statistics. But there are also statistics that tell you that can describe the whole network, or that find you communities or clusters that use different algorithms to find find nodes that behave similarly. The whole network statistics can be like, is it a dense network? Are the nodes very much connected with each other, or are there just communities? Are the communities connected? You usually see it on the in the graph, but the graph is based on these numbers. So you can just quantify it, how much the network tends to building communities, how well the networks are interconnected and stuff like this. And now we are going to focus on the node-wise statistics. The first one to name would probably be the node degree centrality. We are talking about this node n, and its degree is the number of edges it has. So generally, the central degree of node n is 5. 1, 2, 3, 4, 5. If we care about the direction with which we usually do in a directed graph, then we want to count the number of the incoming edges and the outcoming edges separately. This is the in degree centrality. So n has in degree 4, right? 1, 2, 3, 4 go into, and 1 goes out. So the node n's out degree centrality would be 1. If we count it like this, then for instance, we could say that Chile has that people from 3 countries, from four countries, go to Chile, and from Chile they only travel to 1 country. But this doesn't tell us really how many of these people are, and it could matter whether, from this country we have 10 times as many people as from these countries, etc. And to take this into account, there's something called weighted degree. And of course, you have weighted in degree and weighted out degree. And it takes into account the numbers that are in the edges. In our case, that's the path number, no gender path. So the not weighted in degree of n would be 4, while the weighted in degree would be somewhat more than 4. Because if this is 1 and this is 1 and this is 1 and this is 10, then it's going to be something else. Besides this simple centrality measure, there's also something called eigenvector centrality. It's the degree centrality that takes into account that how well these nodes of node n are connected with other nodes. So it's also a sort of weighted degree centrality, only it doesn't care about the thickness of this arrow, of this edge, but it cares about the number of other edges here. And the eigenvector centrality degree of node n is the higher, the better connected, the more edges its neighbor nodes have. You can imagine it as in the society that knowing influential people is more important than knowing many people. You can know a few influential people and you get better job, get a better job or more friends and blah 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 than if you just know any people. Then there's another statistics called betweenness, and that also says something how important the node is, but from a different perspective. It counts the times, how many times this node n connects to 2 nodes, like through this node to how many paths you can take through this node. And it's all possible combinations, right? So it would be this one, these 2 nodes, and these 2 nodes, and these, and these, and these. So although we have just 4 neighbors of node n, its betweenness is 6, because you can make 6 connections through this node. So you see the numbers differ, and it when you want to filter or extract nodes that are most important for you or most important for the research question, you have to make a decision here what sort of high degree you mean. How this is computed, you don't actually have to care much, because you can open the Windows statistics and just push buttons, and you get it from Gephi for free. So here we are in the overview, or you can have it in the data laboratory as well. And you open the statistics panel, and it's going to look like this. It's going to offer you, let me see if I can make this larger. You can in your computers. or let me show it here to you. Well, I'm not sure if that's better. I would probably have to. Well, it's a bit larger, I think. So these are statistics that it computes for you, and I find it, well, here slightly misleading when talking. Well, so when you they offer you something called network overview, community detection, that's the clusters, and node overview, while many of those node characteristics that I just presented to you are hidden in the network overview. That's what I wanted to show you. So those ones we are interested in are the network overview, average degree, and average weighted degree. It makes sense, since to compute the average, you have to compute all of them first. So it just does it and doesn't throw these individual values away, but it keeps them in the network overview. And here is the eigenvector centrality that is in the that's in the node overview. All right, so we pushed the buttons, and we got the in degree column, out degree column in the nodes here, just the simple degree and eigenvector centrality. And also, well, later we got the weighted degree, weighted out, and weighted in degree as well. There you can see that they sum to add to 9, 5 in and 4 out, etc. And the eigenvector centrality is not intelligible really here from what you see. A nice thing about this is that you can here export the entire spreadsheet. So if you want to make, well, if you want to visualize those statistics in a different way than in a network, then you just download your original data table, your original nodes table, enriched with new columns. When you push the buttons, then you also get a report with distribution plots that helps you decide whether the nodes, whether you can discriminate between the nodes based on that statistics. So when we look at the in degree distribution and out degree distribution, which in our case translate to sort of most desired countries, meaning that people from most countries come there, or most abandoned countries, meaning just that from there people flee to many other countries. You can see their distributions here. And indeed, we have some countries to which people travel a lot. No, sorry. We have the other way around. We have many countries to which people don't travel too much, and just the highest one has the value somewhere between 40 and 45, And the same similar distribution we have with this out degree. So there are definitely some outliers here, or extreme values that would be interesting. You can, of course, filter, download your data spreadsheet and filter everything in the spreadsheet, and then read this in and only display that smaller data set. But you don't need to, because Gephi has built-in filters. Again, it's a window called filters, and when it opens, it looks like this. And you select a feature and drag it here to the queries window, and set the parameters. So I'm going to choose nodes according to their betweenness centrality. Betweenness centrality is a range. It is a continuous variable, or at least I want to treat it as a range. I want those that have betweenness centrality minimally something and more. For instance, this would be my range. I do this interactively. Once you click on the parameter here, it's going to offer you a slider when it's a range, or a multiple selection if it's partition. And there on the slider, you can just adjust the what you want to see. And here, this is very nice. You see how much of the data it captures. This is, if I'm not mistaken, this is not the count, unlike in the distribution plots, but that's simply the the value you see here. But anyway, that's the whole data. And when you set the threshold here, then you lose more than 3/4. Maybe it's something like 75% of the data you lose. So you reduce this to 1/4. And that gives you the greatest migration hubs. That's going to give you Canada, Germany, and by the way, that's the output as a picture, as an image. That's done from the overview, preview. So Germany, Canada, Thailand. The biggest one are United States and United Kingdom, and then we have Italy, France, and Niger. It's Niger, not Nigeria, by the way. If we look at the most abandoned countries, then how would we translate this? So does it mean too many countries or by many people, and not, well, if you just take into account all these parameters, so it should be too many countries and by many people, and at the same time, it shouldn't be these hubs. The biggest hubs are United States and United Kingdom. and these are definitely not the most abandoned countries. So we somehow have to reduce or filter out countries that have many incoming people as well when we want to get the most abandoned countries. So that would mean to reconcile many countries, many people, and not many coming in. Translating this to high weighted out degree and low weighted in degree. So this tells us, like, the combines the story of the number of countries and people, and that would be it. Weighted in degree, many from many countries coming in, weighted out degree. Here I'm going to zoom in on the syntax of the queries. Before, you saw a query that only concerned one parameter, and that was the betweenness centrality. It is here, and the query the query here models a hierarchy, actually. Within this range, you can also find you can take this filter and add a filter on top of this. So from these, give me just those that do something else. Partition means they are just Asia, or they are something like this. You would just put it there, and it tells you drag subfilter here. Then it invites you to filter out again things from this one. But this is not our case. We have two sets of countries. Those that have extremely low incoming income weighted in degree, and those that have high weighted out degree, but they can they can have only a small overlap, right? We don't find, if we first say it has to be a country with high in degree or high out degree, then we sort of lose something in the end. So it's better to say, I want to make these two independent and see their independently and see their overlap. And you just conceive this as two sets and their intersection. So first you choose from operators. There's one operator. So you choose an operator, which is this set operation, where you just want to have the intersection, and then the intersection of what? And that's the sub filter of this operator filter. And there you put your range weighted out degree, and I said betweenness centrality because I didn't want it to be a hub, right? And these are at the same level, right? I am not taking just weighted out degree and from them those that have low betweenness centrality, but I am taking their intersection. Here I have not reduced the betweenness centrality yet, but very very slightly. I've lost only one country. And by this, when you then you just play around with the sliders and you watch in the overview, you watch the network shrink and grow, and you just stop the sliders where you like it, or where it tells the story that you want it to tell. So in this, I was asking for the most desired countries, which would again translate into low out degree, like most desired in the sense that everyone wants in and no one wants out anymore. So that would be, again, weighted out degree or betweenness. They should be low, but they should have high weighted in degree. So from many countries and by many people. And you know what the most desired countries on the earth are? I think the first one was Greece, and then it was Germany and United Kingdom. So these are the most desired countries. We have a bit of time, so I can show you the whole thing live again. So this was my data table. I imported the spreadsheet here and edges. Then, and that was it. I called this workspace country 01. Then I was playing with the appearance, where I mapped the color on nodes by continents and color and I also colored the edges. Colored the edges like this, and so on. There, I was able to play around with the size of the labels, and obviously I could have chosen a different font family. This would be about the size of the edges. This would make them visible or not. This would hide or display the labels of the nodes. Here you can take a screenshot of what you see. And let me show you the interaction with the plot. When you right-click with your mouse, you can move the entire graph around. When you roll the mouse, then you can zoom in and out. And when you want to center on the graph in its original size, you select this looking glass here. Now about this dragging here. There are three sorts of dragging nodes or mouse selection nodes. This produces a small such a spot, and whatever whatever you highlight with this spot becomes selected. And you can configure the size of this spot here, or you can say that it's proportional to the zoom. So it's going to grow with this. It's very easy to change as you see it. So so you can easily use it to select different individual nodes. I think that you can, and oh, here you see as well these ears, small ears on that. That means the travel within the country. Very small diameter, not proportional to zoom. So when some of them work in such a way that the selection only lasts. Oh, and you can configure how many nodes you want to see together with that other node, and by default it's their neighbors. So here it's displaying the neighbors, and some of these even keep the selection. Oh, this one keeps it. So the mouse doesn't, but when you select something with a square, then you see that it holds the selection. The selection is kept even when I release the mouse. And this little hand here, this is the node dragging. When I take a node here, and I can just pull it out the network. And this one and stuff. And then it's not going to move. Then I'm going to free it. And oh, I actually haven't found a button to place it exactly on the place where it was. Anyway, when you mess around with a graph and you just want to destroy it again, then you go to a random layout here, press run, and it creates it returns to the original one. Only now you have to again play with the play around with the size of the nodes and thickness of the edges. So this would be after the manipulation. This would be manipulated. Manipulated the force atlas layout. I drew Syria out of it just to see it better, and now I can see all the better all the countries that are connected to Syria. This would be the Fruchterman Rheingold again. That's the Irfan Hu. And oh, I wanted to show you the here. that's what helped me to the original force atlas was very, very dense, and it didn't help to run the expansion on it. It just made it bigger, but it was still very dense. So it needed something, that sounds like make the spaces bigger. So age weight influence made it was the thing that helped most. When I increased the influence of the weight of the edge weight, how many people traveled there, then the bigger the weight, the more far apart the nodes were. So that's what I found out. Normalizing edge weights helped as well, and dissuading hubs, that the hubs shouldn't be together. This is a hub, not Syria, and that was it. That was what helped the most. So this one was incredibly dense, and expansion helped. There I have the statistics, and once you run the statistics, then you can map things here on the statistics as well. So that's the expanded Van Hoe. And here are the filters. So these are the most important hubs. When you click on preview, then you have always to refresh the preview, and it shows the whole network, but it gives you the names, the labels of the hubs, which I found useful, sort of. But here I could as well have all the other nodes disappear. That's the same thing with the most abandoned countries. And this was interesting. The most abandoned countries, you have also Canada and Germany among them, and not so much, and not even not even Syria, which otherwise was clearly one of them. And I can only speculate. I didn't have the time to rerun all the computations and draw all these workspaces again. But I think that it is because the immense travel within Syria. It has immensely many people had destination and origin country Syria, and I think that this just skewed the numbers very much. And the numbers are computed for the graph as you imported it. And if you remember, I ticked that I wanted the self loops there as well. You can, in the filters, you can say that you don't want self loops to be displayed there, but it doesn't help you if it doesn't change the numbers. So if the numbers are based on weights on self loops, then this is not going to help, and that's most likely what happened here. All right. So that's about what I wanted to tell you about networks. There's no homework from this, but you have the whole this whole thing at your disposal, and and the Gephi file as well. And next time, I'm going to show you pretty much the same thing, only we will combine it with the information extraction from the migrant stories corpus, and we will draw a network of how people talk about organizations that were involved in their story, and how to extract the organizations from the corpus, and we will run again we will visualize their stories with respect to the organizations they involved in their travel. So I hope it was somehow helpful, and if you have any questions, just please ask me. All right, so if there are no questions, see you next week.
Thank you, Sylvia. Thank you. Goodbye.
Thank you very much. Bye. Dziękuję moc krát.